All right, so now that we covered the basic introduction to permutation importance, let's take a look at some code examples to see how we can use permutation importance in practice. Yeah, and as always, I also have the code examples in Jupyter Notebooks linked below the video. And also, like always, we will be working with the Wine dataset again, just to keep things simple. So the Wine dataset again is a dataset consisting of 13 columns, and here is an overview of how the first 5 wine rows look like. So there are 3 classes, class 1, 2, and 3, and there are 13 columns, but not all the columns are shown here due to space constraints. But yeah, we won't be discussing this wine dataset in too much detail because we have seen that so many times before. Yeah, and then also, like always, we will be splitting the data set into a training and a test set. So here what we're doing is we're taking the data set, except the first column, which is the label column. So we will be splitting the data set into a training and a test set where 30% of the data is used for testing and 70% will be used for training correspondingly. Notice here that we are not creating any validation set. So it's just my personal opinion, but I don't think we need necessarily a validation set if we compute the permutation performance. Because yeah, usually we should keep our test set independent. But yeah, if you think back of how permutation performance works based on the previous video, we are here only looking at the drop of performance when we permute a feature column. So we are not really recomputing the test accuracy. We are just using the test set for looking at how much the performance would drop if we shuffle a column. Yeah, we are still in the setup stage here. So here in this slide, we are preparing our model. And in fact, here it's a random forest classifier. So in the previous video, we learned that permutation importance is a model agnostic method. That means we can compute that for any type of model. However, we are using here a random forest so that we can then compare the permutation importance to the random forest impurity-based performance, which might be an interesting comparison. So here we are setting up a random forest classifier with 100 trees, and yeah, we're fitting it to the training set, and here is just the accuracy computation, and we see actually here that the training accuracy is 100% and the test accuracy is also 100%, which indicates that this is actually a pretty good model. Or it could also just indicate that the dataset is pretty easy to classify. One thing I wanted to note here also is that when we compute the permutation importance, it's kind of like important to have a very well-performing model if we want to interpret the feature importance as a general feature importance. Because yeah, if we don't have a model that performs well, we might find out what features the model relies on the most, but it doesn't really tell us, let's say, how important the feature is in the context of the target variable if the model is not very accurate. So, and before we look at the permutation importance, just for reference, again, here is the impurity-based importance. So this is the random forest impurity-based importance that we have discussed already in a previous video. Again, this is just for reference where we access this feature importance attribute after fitting the model. Then we are applying arcsort so that we are obtaining the sorting order of the importance values from the largest to smallest. So from largest to smallest. And then what we are doing here is we are sorting these importance values. Here, these importance values, we are sorting them using our indices from largest to smallest. And then we do the same thing for the column names. So these are our feature names. Here we are also sorting them using our sort indices here. So here and here. So in that case, why do we do that? That's so that we can have the feature importance in descending order, and we have the corresponding names here, which is usually quite convenient. So we can say proline is the most important feature for the random forest based on impurity, then flavonoids is the second most important, and so forth. Now comes the interesting part. So here we are now computing the permutation importance. We are using MLExtend for that because this is a function I have implemented a long time ago. Later on, I will also show you that we can nowadays also do that in scikit-learn. So, but just for reference, because I'm also more familiar with that one, we are using feature importance permutation from MLExtend. So why is the name so weird? Why is it called feature importance permutation and not feature permutation importance? Why is it flipped? So as far as I recall, I mean, it has been many years ago, I wanted to call it or I wanted to have multiple feature importance methods. So in general, I wanted to have multiple feature importance methods. And this basically here means feature importance by permutation or feature importance via permutation or something like that. In any case, so how this function works is after importing it, we call it with different arguments. So one is the predict method. So this is just a method that performs a class label prediction, for example. So here we use the forest predict method. So the forest is the random forest that we fit on the previous slide. And then we provide it with a data set. Here we use the test set. Notice we could also use, if we have one, a validation set. But I think personally that using a test set for that is fine because we're not really reusing the test set on different models or something like that. We assume here we have a final model and we just want to see or find out how our final model uses the different features in the data set. Then we can use a metric. So here we use the classification accuracy and we set a number of rounds. So this is how many times we repeat the permutation of the column like we discussed in the last video. So here we use 50 rounds and we start with a random seed of 0. And this is essentially it. All you need is a predict method, a data set, what metric we want to use, and then the number of rounds. And so a very straightforward function. And then we can plot the feature importances. So there is this imp all attribute and the imp val attribute that the function returned. So these are all the importance values that are computed. So when we have 50 repetitions, we have 50 times the number of features. Let's call the number of features m. We have 50 times m different values. And over these 50, we could then compute the standard deviation for each of the m features. And this is what I'm doing here with std. So I'm computing the standard deviation over these 50 runs for each of the m features. And the imp vals are already the importance values, which are essentially the means of these. So imp vals are essentially just numpy mean imp all, and then go back, axis equals 1. So this would be the imp vals. It's already pre-computed in the function though. Then we are again using argsort to obtain the sort indices from largest to smallest. This is similar to what we have done previously for the impurity-based random forest feature importance. And then all the plotting code here is identical. So here the only difference is that instead of using the impurity-based importance values, we are using now our permutation-based importance values. And in addition, because we have these standard deviations, we are also plotting the standard deviations as error bars. So here, then in the lower right corner, we have our feature importance plot. So here we have the features again in descending order with color intensity as the most important feature. And then these error bars here are our standard deviations. Yeah, let's now look at the two methods for computing feature importance side by side. So on the left-hand side here, I have the random forest impurity-based feature importance. And on the right-hand side, I have the random forest feature importance via permutation importance. And often, based on my project experience, I find that these give very consistent results, which means that the ranking order of the features, the most important features, is often very similar or even identical. Here we can see it's not quite the case. So we see, for example, proline is top 1 here. Here proline is top 2. Color intensity is top 1 here. And color intensity is top 3 here. However, if we look at, let's say, the top 6 most important features here, the features that have some value here in the permutation importance, we can see that these are relatively consistent with impurity-based feature importances. So here, these 6, if I see that correctly, are the same. So the order within the 6 is slightly different, but overall, yeah, these 6 are also represented here as the top 6. So at least there is some consistency. So for example, we can still say color intensity, proline, flavonoids are the most important ones. If we look, for example, at the top 3 here, it's just slightly different ordering here. And also one note I have here at the bottom is, personally, I find it most useful not to scale the permutation importances. So random forest impurity-based feature importance is usually scaled such that the columns sum up to 1. So the columns here, the sum of the columns, that's called the feature importances Fi, they sum up to 1. And this is not the case here on the right-hand side for the permutation importance. So here, the permutation importance represents the average drop in our metric. Here we use the accuracy. And I find this actually more useful than scaling it, because here I can say, okay, if I permute color intensity, my performance, my random forest performance drops by 10%, which is actually quite useful to know, I find. Yeah, now that I've shown you how to compute the permutation importance in MLExtend, for completeness, I also wanted to mention that nowadays you can also compute the permutation importance in scikit-learn. And as you might expect, so the function name is permutation importance. And the behavior of that function is very similar to MLExtend. So here again, for reference, we are fitting a random forest classifier. And then once we have fit the classifier, we can provide it as estimator to the permutation importance function, provide our data set, scoring function, for example, accuracy, and set the number of repeats, so the repetitions, the number of rounds. And this here will behave exactly like the MLExtend function. I mean, there are tiny differences. For example, here we provide the estimator instead of the predict method. And also the name here is slightly different. So instead of metric, it's called scoring and so forth. But looking at the results here, side by side, you can see, the MLExtend and the scikit-learn functions almost provide identical results. I think there are some slight differences. You can see it's somewhat slightly different, but it has maybe something to do with the random state here or something like that. But I wouldn't worry about it too much. So these two methods, are almost identical. Yeah, now we actually know how to use permutation importance in Python using either MLExtend and scikit-learn, which is awesome. However, before I finish this video, I wanted to show you a few more useful things. So one is using random features as a control. So what I find technically or in practice relatively useful is to include a random feature in the dataset as a control when we compute the permutation importance, because that can give us an idea of what is a meaningful feature importance and what it is not. So what I'm doing here is I'm creating a random column. So what I have here is x1. It's data sampled from a random normal distribution, and it has the same size as our, let's say, number of rows in the training set. And so I'm essentially, if I have a training set, let's say with 200 examples, I'm sampling 200 examples from a random normal distribution, and I'm reshaping it to -1, 1. And this is so that I can concatenate it with the original training set. And then I'm doing also the same thing for the test set here. So again, I'm sampling from a random normal distribution here, same size as the test set. So I have now two random vectors that have the same number of examples as the training or the test set. And then here I'm stacking it with my training set or my test set. And then I will basically have another feature column. So originally my data set had 13 columns. So we had originally 13 feature columns. And with this extra column, we have now 14 feature columns. So before, let's say my test set was 54 examples with 13 columns. And with this random column, I have now 14 columns in my test set. Yeah, and then what I do is just running the permutation performance as usual. So I have my permutation importance here, let's say from scikit-learn. I import my random forest classifier, initiate my random forest classifier, fit it to the training set. And here notice now I have the modified training set with this random feature. But everything here is the same as before when I used the scikit-learn permutation importance. And then here at the bottom, yeah, I'm plotting the permutation importance. And on the right-hand side is my plot. So the result of executing this code here below, which I don't necessarily need to discuss in detail because, yeah, it's the same as before. And what you can see now is that we have this additional random column. Here it's not very interesting because it's 0. Actually, that's what we might expect. But in certain types of models, depends on your data set, you might find that the random column has some value here, some drop. And this kind of like gives us a threshold of feature importances. So sometimes you might find that some importance values are, let's say, having some value here, and then something like that. And you might wonder whether this is a meaningful feature importance or whether it's just maybe due to chance or due to a random effect. And when we have this random column, we can actually tell what our threshold here might be. So if I have something like of this magnitude, I might argue, okay, everything below this one is like a meaningless feature importance. So the only important features might be those 3, for example. Yeah, and another thing I wanted to bring up is how we deal with correlated features. So one problem with permutation importance is similar to impurity-based performances is if we have collinear features or highly correlated features. So what happens is that these will share the importance. So to kind of illustrate this, I have an example here where we have, or where I'm creating a data set where we have highly correlated features. So yeah, this is a kind of synthetic data set. So what I'm doing here is, first of all, I'm creating class labels. So I'm initiating an array of 1000 zeros and set 500 of those to 1. So what I have then is basically an array where I have a lot of zeros, 500, and then 500 ones as my array, as my labels. Then I draw 1000 examples from a random normal distribution. That's my first feature. And then I'm creating a second feature here where I draw, again, 500 data points from a random normal distribution and assign it to the first 500 values. And then I'm again drawing 500 values from a random normal distribution. But now what I'm doing is I'm adding the number 4. So if we would visualize that as, let's say, a histogram or let's say a density plot, how it would look like is if we have, let's say, a 0 here, would look like this. And then we have, let's say, the 4 here. That would basically look like this. We have basically two different normal distributions. One is shifted by the value of 4. The mean is shifted to the right by 4 units here. And so why am I doing that is so that we have the first 500 labels of 0 corresponding to this first peak, and the ones, let's say, corresponding to the second peak, so that the classifier can actually learn something, like, so that it is possible essentially from this data set here to distinguish between the labels 0 and the labels 1 here. And in addition, I'm also creating another feature here. So here I'm creating another feature x3, where x3 is essentially just a copy of x2. So these should be perfectly correlated then, right? And then lastly, I'm arranging that into a design matrix, so a regular representation for scikit-learn. I'm using swap axes so that I have the 1,000 here, the 1,000 examples as rows, and the 3 feature columns. Otherwise, it would be 3 1,000, which is not what we want. So this is why I'm using swap axes after calling vstack when I'm stacking these features. Okay, so this is my artificial data set where I have perfectly correlated features here in x3 and x2. Yeah, then I'm preparing my data set, and like always, I'm splitting it into a training and a test set, using 30% for testing and 70% for training. Yeah, then I'm fitting my random forest classifier that I initialized here. So I'm fitting it to the training set. And then looking at the performance on the training set, I find it has 99.7% accuracy on the training set and 97.6% accuracy on the test set. So it's actually a pretty good model, but again, the data set was also pretty simple because we had this one feature where the feature overlap maybe a little bit here, but not too much. So it should be possible to classify it as class 1 and class 0 based on one of the features. So what I also find often useful in practice is to just look at the correlation coefficients. So I'm just noticing I skipped one line of code here. So I was computing the Pearson correlation coefficient from or using NumPy. Like this. It should be in the code notebook that I uploaded. Yeah, you have to be always careful in when you use NumPy. Always be careful to transpose the design matrix so that you get a 3x3 correlation matrix. Otherwise, you will get a correlation matrix for the training examples, let's say 150 times 150. However, in SciPy, you usually don't have to transpose. So what I usually do in practice after transposing, I look at the shape of the correlation matrix just to make sure the shape is the number of features times the number of features. In any case, so looking at the correlation coefficients here, what we can see is, of course, that the diagonal is always 1. So, by the way, perfect correlation is always, is 1. That's the highest correlation we can achieve. No correlation would be a value of 0, and perfect negative correlation would be minus 1.0. So what we can see here is that let's read it from here. Feature index 0 is perfectly correlated with feature 1. So these 1 and 0 here, they are perfectly correlated. And 0 and 2 are, let's say, there's no correlation between the two. And this makes sense because this one here, feature 2, I think I provided them in the reverse order. x3, x2, x1. When I stacked, I did the NumPy vstack, I had them in reverse order. So this feature here is our random feature, the feature with index 2. So this, let me use a different color. So this is our random feature. And for our random feature, we would expect that the random feature is not correlated to feature 1 or feature 0. However, these two are correlated with each other, right? Because we created just a copy essentially where we have x3 equals to x2. So in feature indices, it would be feature index 0 is the same as feature index 1, or the features are identical essentially. So it's just for double checking which features are correlated. And here we are just confirming that 2 features are correlated and 1 feature is not correlated. All right, let's now compute the feature importance. Like before, we are using our fitted random forest, which has been fitted to our new data set here, 50 rounds, and using the accuracy as the metric. And as we can see here, as we would expect, because feature index 1 and 0, the features corresponding to those, are perfectly correlated, we can see that they are sharing the feature importance. So they have exactly the same feature importance, and the random feature, feature 2 here, feature index 2, has no importance, so no drop in accuracy, which is also what we might expect because, there is no correlation between the class labels and this random feature that we created. Only those 2 features are meaningful here. And you can see they are sharing the importance here. Both have equal performance drops if we shuffle. Now, just as an experiment, so the code is not shown here, but if I would remove one of the features, what we would see is that the other feature, so if I remove, for example, this feature, what we see is that the other feature takes over. So it's almost twice the performance. So here we have let's say 0.25 approximately and 0.25. And if I remove that feature, so if I get rid of this one, we will find that we get almost twice the performance. And the reason is that these 2 features are equally important, right? So and if these are equally important, they share the permutation importance because the random forest could pick either this one or this one for splitting the nodes and would get exactly the same results because they are perfectly correlated. So the bottom line here is it's always a good idea to check the correlation among features if you are interested in using permutation importance. Because if you find that 2 features have a very high correlation and you want to really, let's say, interpret the permutation importance, it might make sense to actually remove one of these features because then it tells you a little bit more about how important the feature really is compared to other features in that data set. All right, we reached the end of this video, which was probably, again, longer than I intended. So this was it for permutation importance. And in the next video, we will look at sequential feature selection, which is, by the way, my favorite feature selection method. So this is going to be fun. And then we will also take a look at a code example of how we can use sequential feature selection.